All right, these are the answers to the first 6 of the 12 additional student problems for Module 7. We'll do these first 6 in the first video and the second 6 in the second video. So number 1, which of the following is a conjugate acid-base pair? So a conjugate acid-base pair differs just really by the presence or the lack of one hydrogen, and the root compound has to be the same. So to find our answer, we just need to see which one of these differs by the presence of a single hydrogen atom. Okay, and as we've seen many times throughout chemistry, sometimes if you don't know what the answer is, you know what the answer is not. So that's a valid approach for finding the solution here. So let's take a look and see what we have. Okay, answer A does not differ by one hydrogen. Yes, there is an absence of a hydrogen, but there's also the presence of an oxygen. So this is not the same root compound, so this cannot be correct. When we look at B, it is the same root compound, sulfate, but it differs by 2 hydrogens, so it also can't be correct. When we look at answer D, it also differs by 2 hydrogens, so cannot be correct. And we are left with 2 possibilities, but if we look at answer C, it does differ by the presence or absence of 1 hydrogen. So in fact, answer C is our correct answer for this problem. Number 2, for the stepwise dissociation of aqueous phosphoric acid, H3PO4, which of the following is not a conjugate acid-base pair? So again, we're looking for a pair of molecules or ions whose difference is just the result of a lack of 1 hydrogen, and the root compound must be the same. So to see which one of these pairs does not differ by a single H, we just compare things. So answer A differs by 1 hydrogen. We're looking for something that is not a conjugate acid-base pair. A is a conjugate acid-base pair, so cannot be correct. Answer B also differs by 1, so cannot be correct. Answer C differs by 1, so cannot be correct. Answer D, however, differs by 2 hydrogens, and so that is correct. It is not a conjugate acid-base pair. We go back and check E. Do they differ by a single H? And the answer is yes, they do. So E cannot be correct. Once again, giving us answer D as the valid answer for problem number 2. Problem number 3. We want to see if we can rank these in order of base strength when given the Kas. Now this is a little bit of a challenge because we're given Kas, but we really need Kbs. But really, they're related to each other. Ka times Kb is equal to 1 times 10 to the minus 14th, which is the dissociation constant for water. So really, we can rearrange this expression and get that Kb is just 1e minus 14 divided by Ka. And so what that means is the acid with the smallest Ka is going to have a conjugate base with the largest Kb. Well, that's pretty convenient because that makes our job pretty easy. And if we look at this red box, this is nothing more than the items above it. The conjugate base of nitrous acid is the nitrite ion. The conjugate base of hydrofluoric acid is the fluoride ion, and the conjugate base of hydrocyanic acid is the cyanide ion. We can compute the Kbs by 1e minus 14th divided by the respective Kas, and I've just tabulated them there. So we can put these in order and go, well, I can see right off the bat that cyanide will have the highest Kb, followed by nitrite and fluoride, but then there's this matter of the chloride. What do I do with that? Well, it turns out since chloride is the conjugate base of a very, very strong acid, it's just going to have the smallest Kb, because essentially the Ka is a very, very, very large number. So 1e minus 14 divided by a very large number is a very, very small number. So that makes the chloride ion our absolutely weakest base. And so now we can look at this and go, well, that means that answer A is the correct answer. Moving to number 4, we want to calculate the hydronium ion concentration in a solution that has a pH of 11.7. This is just using the definition of pH, and we kind of work the problem backwards. We want to find the value of H+. We know our equation for pH is the negative logarithm of the concentration, the molarity of the H+. So if we rearrange this with a little bit of algebra, we see that the H+ concentration is just 10 raised to the negative pH. Well, this makes the problem pretty easy, and we get 2 times 10 to the minus 12. Now, if you did not have a calculator, you could also look at this problem and go, well, wait a second. Exactly neutral, a pH of 7 is going to be neutral, and so this pH that is significantly greater than 7 by a factor of 10,000 is not going to be very acidic. In fact, it's going to have a very low concentration of hydronium ion. So right off the bat, you can eliminate A, B, and C. That leaves you with D or E. The answer might be none of these, and for that, you're going to need to do the calculation. Okay, so we do that, and we get 2 times 10 to the minus 12, so we get answer D. All right, moving to number 5, we want to calculate the pH of a 0.250 molar HNO3 nitric acid solution. This is nitric acid, one of our 6 strong acids. So there's not an equilibrium. It's a strictly 100% ionization problem. And so we can proceed directly to the pH calculation, because we know 1 mole of HNO3, or 1 molarity of HNO3, is going to give 1 molarity of H+. In our case, we have 0.25. So we just take the negative logarithm of 0.250, and I get an answer of 0.602. So clearly answer A is the right one. All right, that takes us to problem 6, the last one in this short video. Which of the following indicates the most acidic solution? Now, we've got a variety of expressions here. We've got to put them all on a level playing field so we can compare them. Okay, you can put them all in OH minus, you can put them all in H plus, you can put them in pH, you can put them in POH. 4 different ways. We know that most acidic means the one with the highest molarity of H plus hydronium ion, so the lowest pH. So therefore, let's put everything in a pH scale. We know that pH plus POH is 14, and we know that H plus concentration times OH minus concentration is 1 times 10 to the minus 14th. And with those, we can get them all on the same units. We can compare them, okay? So that means for A, using our equation that pH plus POH is 14, we can get that pH is equal to 13.7, because I'm going to take 14 minus the logarithm of 0.5. All right, for B, I just take the negative logarithm of 0.3, I get 0.52. For C, pH is just 14 minus the POH, or 8.1. D is already in pH units. And E, I've got to take the negative logarithm of 1e minus 4, and I get 4. So now everything is in the same units of pH, and I can compare them, and I see that answer B is in fact the strongest acid, because it has the lowest numerical value of pH. That concludes this short video. We'll do another video for problems 7 through 12.